Well, hello, everybody. We'll get started now. The title of this presentation is the Perma Pure MD 700 dryer for particle analysis. Uh, Thank you all very much for coming. Just for a couple of housekeeping points before we get started, Zoom has a chat box, so if you have any questions during the presentation, you can put your questions in the chat box. And I will make sure we have ample time at the end of the presentation to answer any of your technical questions. I want to introduce myself. I'm Gene Bohensky, the Director of Application and Partner Learning. I've been with Perma Pure for about 8 years now. I started as the Director of OEM Sales, and as part of my job was to go and really learn from our customers what they were doing with our products. One of the things I discovered is that a lot more people were using our dryers for particle analysis and aerosol research than we understood in the past. And as part of that process, I was involved in the development of the MD700 dryer for particle analysis and saw that product come on to the market and is now a solid part of our product line. And this presentation is going to cover that product, its applications, why the product was developed, and how it was tested. So to give you a little bit of background on it. And with that, I will also provide all the things I've learned in the marketplace since then, which has been very interesting. So as an introduction, for over 25 years, Perma Pure's Nafion gas sample dryers have been used for a wide range of particle analysis applications in analysis, experiments, and design into many analyzers. And the main application is to control the humidity for improved accuracy and consistency, as the particle size and weight are dependent on the relative humidity of the air in which the particles are suspended. The MD700 dryer was designed specifically for particle analysis applications to limit particle losses. That's its main reason for existence, was to limit particle losses when compared with our standard Perma Pure dryers. So questions we will answer today. What is the MD700 Nafion gas sample dryer and how does it work? What makes it special for particle analysis applications? How do I integrate it correctly, measure the effectiveness of its setup, and optimize its performance? And how do I connect or generate a purge gas with a moisture level low enough to dry the sample effectively? So first things first, as I'm apt to do, let's review the basics of humidity and dew point. I know for a lot of you, this is a very simple or academic point, but I want to review this to get our minds engaged with the concepts so that when we are presented with the balance of the presentation, we'll be ready for the concepts. So let's first talk about relative humidity. Relative humidity is the amount of water present in the air expressed as a percentage of the amount needed for saturation at the same temperature, or the amount the air can hold. So it's a percentage of the capacity of the air at that given temperature. The relative humidity represents how close the air is to saturation. It cannot be measured by a measured value, as the amount changes with temperature. Saturated air will have a relative humidity of 100%. For example, you need relative humidity of 100% to have rain form in clouds or water to condense. In the particle analysis world, relative humidity is what affects the results, as the particle size is directly affected by the relative humidity, and is what is tracked with the measurements, not the dew point or not the actual moisture level, which is interesting because when you do gas analysis, it's the actual amount of water that is present that affects the measurements. And as a result, we always track the performance of our dryers in terms of dew point. But in terms of the particle analysis world, it's the relative humidity, and that is the amount of water is changing because the temperature changes. So there is a mental change here in looking at the measurements. So the dew point is the temperature of the air which is needed for condensation or dew at that particular temperature. So if you take a glass of ice water and it develops condensation on the glass surface, The air on the glass has cooled to its dew point, and the water vapor has condensed and created dew. The dew point can be used to calculate how much water vapor is in the air and can be represented by either a value in parts per million or as a pressure. We use this as a representation of the actual amount of water in the air. It's really the same as absolute humidity if we have a standard atmospheric pressure of 1 bar. Obviously, the dew point can change depending on the pressure, but here we're going to consider the pressure of the atmosphere to be constant. So let's look at the relationship between relative humidity and dew point. This basically shows how the capacity of the air to hold water increases as the air is warmed and decreases as it is cooled. So that's some air temperatures there. That's in Fahrenheit. 55 degrees is roughly 15 degrees C. And at the top end, 80 degrees C is roughly 80 degrees F is roughly 25 degrees C. So you can see how the capacity of the air increases. For this example, we're going to make sure the amount of water in the air does not change with the change in air temperature, as it normally doesn't through temperature changes in the day. But let's overlay the two. You could see that at the 15 degrees C or 55 degrees Fahrenheit, when you overlay the two where you have 100% relative humidity, at the top end, at 80 degrees Fahrenheit or 25 degrees C, that equates to 42% relative humidity. So that's actually a very dry day. That feels dry and nice to be out in that kind of relative humidity. But at the same time, that same amount of water is 100% relative humidity at the lower temperature. So as a review of relative humidity, given a constant moisture content or dew point in the air, as temperature rises, relative humidity falls, and as temperature falls, relative humidity rises. So let's look at how the dew point varies over the year. These are some of the issues in measuring or doing particle analysis, or that they're going to affect you guys primarily because you're dealing with atmospheric measurements, especially if you're doing anything outside or anything with the environment. What's going to happen over the years, the dew point changes over time, not only from week to week and day to day, which is possible as weather changes, but there is also an overall trend throughout the year that in the warmer months you have a higher dew point or higher water content than in the air than you do in the cooler months. And here's the one that really vexes people doing particle measurements outside. Here's the relationship between dew point and relative humidity and how they vary over 24 hours. So you could see the red curve represents the temperature, your green curve represents your relative humidity, and your blue curve there represents the amount of water in the air or the dew point. So you could see that over a day, the dew point doesn't really change very much. But you have this inverse relationship between temperature and relative humidity, that as the temperature rises through the morning and to the midday, you have your highest temperature of the day, and therefore you also have your lowest relative humidity. And as the day turns into evening and early morning, at 4 a.m., you typically have the lowest temperature and the highest relative humidity. And that's, of course, where if your temperature goes below the dew point, you're going to get condensation everywhere. You're going to get dew that falls everywhere. And as you know, making measurements, whenever you have dew falling in places, you have trouble making measurements. And if you have any electrical enclosures or equipment or sensitive instruments outside, they're all going to get wet. Even inside the enclosure, you have the potential of collecting water. So let's go to the next portion of our presentation and talk about what Nafion is. So all of our gas sample dryers use Nafion tubing, a Nafion polymer precisely. And Nafion is a copolymer of Teflon and sulfonic acid and is highly resistant to chemical attack. Nafion removes water by a first-order kinetic reaction, so equilibrium is reached very quickly, typically within milliseconds. The transfer of moisture is driven by the differential water vapor pressure between the membrane sides in the vapor phase. So we're taking out the water vapor in the vapor phase. And the Nafion permeation selectivity is based on the chemical reactivity, not the size of the molecule. So it is not traditional permeation. And you can take a look at that diagram at the right. You can see the green, red, and yellow jelly beans represent the particles that we are trying to keep intact, and we're going to be analyzing in our particle stream. And those blue spheres, first the blue jelly beans in the tube, and the blue spheres represent the migration of water from the inside of the tube to the outside of the tube. And this transfer of moisture is facilitated by the differential vapor pressure between the membrane sides. And we're talking about just the vapor pressure of water. Now, this is different than regular permeation. When you take a look at regular permeation membranes, they typically operate on the basis of a mechanical permeation. That means you have a screen, kind of like a bug screen, with holes in the screen that match the size of the molecules or components that you want to move through the membrane. And so this is typically a mechanical permeation. That's not what Nafion is. Nafion is a chemical permeation. What's actually happening is that the water becomes part of the material's chemical structure and moves through the lattice of the material from one side of the membrane to the other. Based on that differential vapor pressure, it also requires no energy to happen, as it is a first-order kinetic reaction. So what makes that so special is that is a selective removal of water. That means because it's chemical, we selectively remove that water, and that's what makes the material so valuable in our industry, is because we can remove the water vapor while leaving everything else intact in the sample, and we can do that in the vapor phase without condensing anything out, because you can imagine you can't really condense, you can't use a cooler to condense a particle stream, because you're going to end up creating condensation, and then you're going to lose all your particle analysis. So it's critical that the water is removed in the vapor phase. So let's go to the MD700 dryer for particle analysis in this phase of the presentation. The background here is that, let me just mute all of the people that are in the meeting. So the background is that we understand that controlling the humidity of the air sample is critical to getting consistent results for aerosol and particle analysis across a wide range of ambient conditions, as the particle size, as we said, is affected by the relative humidity. And so the ideal relative humidity for measurement can be 35, 40, or under 50%, depending on the analyzer type, whether it's a PM 2.5 analyzer, a nanoparticle analyzer, a black carbon analyzer, or other aerosol instruments for research. Customer feedback has shown that traditional Nafion tubing gas dryers show high particle losses due to their small pathway diameters, making them unreliable for accurate and repeatable results for many measurements. And so here is an example of particle losses from a multi-tube dryer. That's an old one, where you see how one has been used and all the particles have impacted kind of the center there. They also tend to impact the sides of the insides of the tubes, because the flow of the gas sample tends to become turbulent when you push that gas through those little tiny tubes. So it's this turbulent flow that creates greater diffusion losses and also greater losses in general when you're doing particle analysis measurements. And as a result, these have been used successfully in some applications, but they're not ideal. So our MD700 dryer development goals were as follows. Using the power of Nafion polymer, the MD700 dryer was developed specifically for humidity control. in the PM1, 2.5, or 10 nanoparticle and other aerosol analysis applications to limit particle losses. And the first design design feature is that we use a single tube, large diameter Nafion tube, which is 700 thousandths in diameter, or 17 millimeters, that ensures a laminar sample flow through the dryer at all of the flow rates that are found in the particle analysis world. That means we looked at the top flow rate being that 16.67 liters per minute, or the 1 cubic meter per hour requirement from the standard ambient collection units. We also built it out of an all stainless steel construction to prevent any type of static buildup, so that you have a continuity, electrical continuity through the dryer. The Nafion polymer membrane is physically away from the particle flow path. So we've designed this with really a stainless steel cage inside, and the Nafion sheath is placed over the cage. The cage is what provides the dryer strength, because the thin Nafion tube is not strong enough to, physically strong enough to exist on its own without the cage. And the removal of moisture is done completely in the vapor phase without heating. So no heating is required to control relative humidity. One of the things we've learned is that heating works to some degree, but you also lose your volatiles. And you also have issues if your heating isn't consistent. So we are removing we don't need to heat the sample in order to control relative humidity. And we've developed the dryer with a range of lengths that is available for the wide range of flow rates found in the aerosol and particle analysis field. So our MD700 dryer target markets include PM 2.5 analyzers using the heating method to replace the heater for greater accuracy, aerosol research for any particle size. For nanoparticle analyzers, we've worked with a lot of those manufacturers. They've shown that really the only accurate way to dry a particle stream is with a Nafion a tube, and that's really critical to get accurate results. So the MD700 dryer was designed exclusively for a lot of them. Application benefits include the ability to maintain the relative humidity for consistent measurements during the daily RH cycle, no losses of volatiles, and to replace the desiccant column in a lot of the labs that require a lot of time and effort to do, and cost. So how does the MD700 dryer work? So similar to our other dryers, it's a simple tube and shell design that functions with water vapor, similar to how a heat exchanger transfers heat. Normally, we would recommend that any of these dryers are mounted vertically, because you don't want to have a gravity effect of losing some particles, although it's not so much of an issue in the nanoparticle field. So the sample gas flows through the inside of the tube, as shown there in the dark blue arrow there to the left. So that in this diagram, the sample is flowing in the middle of the tube from the left to the right, and your purge gas is flowing concurrently to that on the outside of the tube from right to left. And those flows are sealed off from each other so they don't mix. The purge gas can be instrument air, another bottle gas, or a vacuum generated by a vacuum pump or other means. And again, it should be mounted in the vertical position. So to prove the unique selling feature, we needed to characterize the losses. So since it was developed to have such low particle losses, we felt it necessary to formally substantiate the claim. And here I want to call out our collaborator, Dr. Ali Wiedenzoller at Tropos Leipzig at the World Calibration Center for aerosol analysis. It was actually his idea that came up with this dryer in the first place. He was building the first prototypes and first limited production for his customers or clients doing aerosol research in the atmosphere, and he's the one that really educated us onto the need to have this product developed for industry. So he was also very kind to provide his calibration lab to us in order to do the testing. So what we did is we characterized the losses for particle sizes of 5 to 40 nanometers at its calibration center. It was determined that sizes larger were determined not to have excess losses over bare tubing, and that measurements would be difficult. So there are standard losses that can be calculated based upon your flow path, and we realized that above with the physical characteristics of the dryer, above 40 nanometers, that difference would be insignificant. So what we did is we looked at net particle loss results and comparative results with bare tubing were generated. So let's go through the method. We'll just explain this a little bit. The laboratory infrastructure at Tropros was used, and it was used for the generation of the silver aerosol particles used to characterize the dryers. So the first part was the aerosol generator. That's for the generation of silver particles. A tube furnace with 3 temperature-controlled heating zones was used. Specific particle size distributions are generated by altering the temperature of the furnace, as shown in the following slide. So you could see that by altering the temperature of the furnace, you can make particles of certain sizes, right? That's how we were able to look at certain sizes. And then from here, we would dilute those parts and sinter them and neutralize them and put them through a DMA, which is a differential mobility analyzer, that allows us to precisely put particles of a known size through the dryer, so with a known size distribution. So after cooling, the silver particles enter the measuring and sintering unit. Before feeding the silver particles to the DMA, they are neutralized. A Tropos short DMA with an aerosol flow of 3 liters a minute and a sheath air of 20 liters a minute was used to select a mono-dispersed particle size. Okay. From there, we had our test Nafion dryer assembly, where the flow was diluted and split into 2 identical flows, one into the MD700 dryer assembly and one into the tube assembly of the same physical configuration of 10 meters of dryers assembled in series. The second was assembled with bare aluminum tubing to serve as a comparison. A length 10 times longer than would normally be installed was chosen to amplify any differences in results, as the calculated theoretical losses are so low. So we needed to extend the dryer to make sure we can get an accurate calculation. So here's what our test setup looks like. These are our rows of our coils of MD700s. You could see we used 8 dryers in a row for 10 meters. Okay, and then we compared that to the same lengths with bare tubing. So here's our test setup. At the end of each line, an identical condensation particle counter, as TSI model 3772, was used to count the number of concentration of silver particles flowing through each test assembly. And particle transmission measurements are corrected for a length and displayed for one dryer versus a straight tube. The losses are highly dependent on the size of the particle being measured, and as I mentioned before, as the particle size increases to 40 nanometers, any losses become insignificant. So here's our raw particle loss results. You can see that through a straight tube, at 40, that's the dP is the diameter of the particle. So at 40 nanometers, your total losses, that's the amount of penetration going through. So 0.986 versus 0.985. It's very little difference. The difference becomes a little bit more pronounced on as you go lower, let's say at 5 nanometers, you're looking at a penetration of 81% versus 75%. So you could see that in a next comparative diagram. This is a graph that shows the difference of excess particle losses. You could see that typically a long dryer like this would be used at 10 liters per minute or even 5 liters per minute. And you could see that these losses at 10 nanometers or less start to become a little bit larger, 2%, 4%, 6%. But really above 20 nanometers, your excess losses are way under 1%, and at 40 nanometers become insignificant. Now then you also have net particle loss results, and you could see there that with the dryer, you could see that also above 20 nanometers, your net loss results are like 1.5%, 2%. And basically we see that in reality, your net particle loss results are roughly, they're roughly under 2% for basically the whole size range. And that really has to do with just the physical properties of the dryer. Nothing actually to do with the Nafion itself. If you put in a bare tube, it would be the same. In many cases, you are substituting a dryer for an equivalent length of bare tube that you're using from where you're collecting your particles to where you're bringing them into your analyzer. So in general, you can say that for most of the applications, the dryer does not provide any excess losses over a comparable bare tube. So here's a drying performance curve of the dryer. Like we stated, the goal was for ambient measurements at all the different flow rates required. Our design goal was to keep the resultant relative humidity below 50%. You could see that we largely do that. And this is also the first time we measured the performance of the dryer using a vacuum pump. So all of our other performance curves use instrument air as your purge gas, but here we're using a vacuum to drive the purge. And this is the first time we've published data on that. And you can see the vacuum level that we did it at. You can go to a deeper vacuum and get even better results than what are shown on the graph. But these are pretty good, a pretty good compromise. And you could see that for most of your applications, you're going to be under 50% on your relative humidity. And here the graph shows relative humidity at outlet on your y-axis and relative humidity at inlet on your x-axis. Here's our product specs and our different flow rates on the right for different sizes, and you'll match the size to your analyzer requirement. We have a temperature rating up to 80 degrees C, so basically it will handle any type of ambient condition. Here's our part numbering system, where we show here our first series. MD means a monotube dryer. Next is your tubing size, and here's your length and material. You have 5 different standard lengths, and we have 2 different purge connector materials. Now this doesn't affect the sample. This is strictly the purge connector. For higher volume applications, we recommend the Kynar purge fittings. This is a cost reduction move, but for any type of lab or analysis application, we recommend the full stainless steel version. We also have a number of connection ends. These are all male compression ends, compression tube ends, either in 10 millimeter, 3/4 of an inch, or 3/8 of an inch are available. So let's review the features and benefits of the dryer. First is low particle losses. Large diameter Nafion tubing maintains a laminar flow of the sample through the dryer. We also eliminate heating. Volatile particulates are preserved in the sample by eliminating the need to heat the sample to control relative humidity. Low service costs. We eliminate the need to repeatedly replace desiccant. Multiple modes of operation. It's designed for use with instrument air, vacuum purge, or partial reflux methods. And stainless steel internal construction and sample pathway. Grounded stainless steel construction eliminates buildup of static charges in the flow path. We also have some other dryers that are used for aerosol sample drying, and I just want to point out what those are. In general, we have multiple small tubes in parallel that may cause significant particle losses, which may or may not be important depending on the application. So we have some people that aren't worried about losses. So for those, you could choose these following products: the MD110 or TT110 tubing. You have flow rates up to 1 liters per minute to preserve low loss laminar flow. We have multi-tube dryers such as the PD07018T. That's 18 tubes of 070 Nafion, or the PD6060Ts. That's 60 tubes of 060 Nafion. Those are larger diameter Nafion tubes than what we normally put in our PDs. We have flow rates to 12 liters per minute, but losses can be 15% with these dryers. Large multi-tube FC100 and 125s, those are our fuel cell humidifiers, believe it or not, are used to dry larger flow rates, over 25 liters per minute for research applications, and you can have losses up to 50% because you have these tiny pathways. That having been said, some customers even use these products to humidify their aerosol streams, and it really largely depends on what you're trying to do with them. And if you have any questions, you can always contact us directly. So let's look at the best practices of understanding the performance of Nafion dryers. This is similar to the best practices that I have provided to you in another presentation, but we're going to use similar slides, but we're going to adjust the content for particle analysis applications. So what affects the performance of the Nafion tubing dryer? The first, as we've mentioned, is the partial vapor pressure of water between the membrane sides. As our friend John Dalton has told us, his law of partial pressures show that the total pressure of a gas mixture is equal to the sum of the partial pressures of the individual gas components. And here we're looking strictly at water. We're looking at the vapor pressure of water only. And the variables that affect that primary factor include the sample gas flow rate, pressure, and water content, and the purge gas flow rate, pressure, and water content. And they only affect the performance insofar that they affect that differential water vapor pressure. It's important to understand because we've had some people think, oh, it's flow rate. I should increase the flow rate. And then they mix atmospheric air with a higher level of water in it, and they wonder why their measurements get worse. So you have to understand the fundamentals behind it. The second is the second performance factor is the membrane operating temperature. With the lower the temperature, the better, particularly at outlet. So here we can see a dryer, and this is actually a SEMS application where the sample is coming in at 100 degrees C with a dew point of 70. And you can see if that whole dryer stays operating at 100 degrees C, that you'll get your best maximum dew point of 35, even if you have dried instrument air as your purge gas. If that instrument air is dried to -40 but heated to 100 degrees C, you're only going to get a 35-degree dew point as your maximum dew point. Now, the second curve there, the yellow curve, shows a 40 degrees C final operating temperature, and that shows your maximum dew point will be 0. And at 20 degrees C, you'll get to your -25. The upshot is for applications, you want to make sure that the end point of your dryer is in a cool application and that will affect measurements. Now, typically in the particle analysis world, we're taking measurements, ambient measurements outside, but if it's in the summertime, it could be 40 degrees C with dew points up to 30. And then you're bringing in that sample into an air-conditioned analyzer hut. There you have the possibility of getting condensation on your lines. So you want to optimize the temperature profile of the gas pathway, is kind of shown here. This also shows the gas coming in from the left and going to the right, and the graph has two lines there. There's a black line for the temperature of the sample as it goes through the dryer, and the red line, which is the dew point of the sample gas as it flows through the dryer. So you want to make sure that that dew point is always below the temperature and that you never have condensation form, okay? That's what's critical to understand. So optimizing the temperature profile of the gas pathway in order to prevent condensation at the inlet, heat the dryer for the first 12 inches or half of the length to prevent the sample gas from condensing in this portion of the dryer. In terms of an analyzer station, that might mean that the top half of the dryer is mounted outside of your analyzer shed. So you have a portion of the dryer mounted outside and a portion mounted inside that is cool. And so you want to make sure that out section of the dryer is cool to get your best performance. We also think about dryer performance over time. The dryer performance can decline over time if the water pathways of the Nafion membrane are affected by the sample or purge gas. If there are any oil or contaminants that are in the air over time, they can collect either on the inside or the outside of the Nafion tubing. In terms of particle analysis, we've seen in general that over time, particles will diffuse and collect onto the sides of the membrane over time and will cause a slow reduction in performance. However, for most applications, this could take years to happen and it might not even be noticeable. But some people still ask us, how long are these dryers are going to last in an application? Where we had one large deployment of dryers in the City of London where we were able to get the data from and understand it. And there we found that in some instances, the dryers needed to be replaced every 6 years. But in a couple of instances where it was really dirty and they were next to a lot of diesel buses and trucks, they needed to replace the dryer every 6 months because it was so filthy. Now that's not going to be most of the applications, but I think that the takeaway is that the dryer performance is going to depend on the application, and a regular maintenance or replacement schedule might be useful. So the next part is methods to integrate a Perma Pure dryer into your analyzer design or scientific experiment, and how to test the performance of your setup. So let's go with drying with a dry purge gas. Here's a typical setup. Here's your MD700 dryer in the center here. You have these dew point measurements. That's DP, dew point for here on the left and on the right. You're going to be measuring the amount of water in the sample before the inlet of the dryer and measuring it after the outlet of the dryer and comparing them and seeing what the performance of the dryer is. Here is your purge gas. This is an instrument air inlet and a needle valve to control flow and your flow meter. Your purge gas flows from right to left, concurrent to the sample flowing left to right. And here it goes into your analyzer for analysis. So typically we recommend a purge gas flow rate of 2 to 3 times of the sample flow to be adjusted as necessary for optimum performance. We recommend instrument quality compressed air that is dried to -40 and oil-free. You can use standard quality compressed air, that is air that hasn't been processed so well, but you need to filter it clean. You can use a local air compressor or use nitrogen or other cylinder gas as your purge gas. The next slide talks about the performance with a vacuum pump. And here for best dryer system performance, the optimum performance point of flow and vacuum level should be achieved as shown in the diagram. So we're overlaying two curves. The curve at the right is the vacuum pump performance curve, flow versus vacuum. And here, what you're looking at is a curve that's like any of the K&F type pumps, diaphragm vacuum pumps. As you restrict the flow, you deepen the vacuum that the pump provides. Overlaid there is the dryer performance curve, dew point versus vacuum. As you restrict that flow, your actual performance of the dryer improves until you reach this optimum point where you have the lowest level of vacuum possible, and at the same time, you have enough flow to actually physically remove the water from the outside of the tubing. It's important to understand that this performance point needs to be found for every dryer and vacuum pump combination. That's also important to understand. Needs to be a found. This is a variable here. And during testing, it might take 15 minutes or more for the dryer performance to stabilize in order to make a determination. So when you're setting up your flows, you're putting it on a test bench, you're going to need to take some time before those measurements settle out. Let's look at drying with atmospheric air under vacuum. This is a similar curve, but a lot of people are doing this because they don't have access to instrument air. And here you could use the atmospheric air as a purge gas if you do this under vacuum. And so you have your needle valve ahead of the dryer or before the purge inlet, and your vacuum gauge is after the purge outlet. You want to restrict the flow so that the vacuum is placed over the dryer. We've seen people that have put the restriction in the wrong place and they got a vacuum, but not over the dryer. Here, I want to make a point that I ran into with a lot of customers. A lot of people have purchased samples of this product and other products, and then they didn't work for them. And they came to us and said, hey, we weren't able to get this work. We don't think it works. It's not going to work for us. Well, we've been making dryers for 40 years, and what we found is that, first of all, it is the material property that drives the drying. So if you're not getting the dryer to work in your application, most likely there's a problem with the way you're connecting up the dryer. And I've seen this a lot of times with customers, that there's some sort of error made in the way this is connected, and months go by and we're not in contact, and the project stalls because of a very small error in the way these things are connected. So if you're not getting the performance you're expecting, please contact us immediately and we'll help you figure out how to connect this up properly. We've seen all kinds of errors. We understand that because this isn't something that you're working with every day. Most people working on analyzers or experiments have other things to deal with, and not using needle valves and vacuum pumps and all this flow equipment to really, they're not using that on a day-to-day basis. So as a result, you can have a lot of errors happen. Here's a couple of versions where you can recycle the sample gas with vacuum. I'm not really sure that's going to be done very often for this application, except this one, splitting the sample gas off and using part of the sample gas to dry as a purge gas. Here you'd probably need to filter it first before you bring it back. But we have a lot of customers that do this type of operation. It provides a very stable dryness level. Just not sure that it's going to be used very often in a particle analysis application. So just want to go through a couple of design and challenges found to customers. Don't let these happen to you. Number one, not understanding the true level of moisture in the sample gas. That's common. Running the hot and wet gas directly into an unheated dryer, causing condensation at the inlet and poor performance. Or installation in the analyzer enclosure where it is so warm that performance is ineffective. A big one is not running the vacuum pump at its optimum performance level. One OEM was able to tweak that and use the same pump and got much better performance. Or mixing a dry purge gas with atmospheric air to increase the purge gas flow rate, reducing the effectiveness of the purge gas. Not installing a long enough dryer. Or using moisture traps in the analyzer in places to trap excess water. Or having the purge gas flow in the same direction as the sample gas. It'll work, but it'll be a lot less effective. Or pulling a vacuum on the purge side without any purge gas flow.